Good morning students. Previously we have started with the topic solenoid and we have studied what are the magnetic field lines and the diagrammatic representation of the solenoid. Today we are studying about Fleming's left hand rule. Now Fleming's left hand rule we will be using in the topic the force acting on the current carrying conductor. Now first we have to study about what is the meaning of the Fleming's left hand rule. For that you have to study about, now we have to take the left hand, and in the left hand we have to study about what are the different directions shown by the thumb, first finger and the second finger. When thumb, first finger and the second finger, they are mutually perpendicular to one another, then the first finger it will show the direction of magnetic field, the second finger it will show the direction of the current, and the thumb it will show the force on the conductor. So we can write down it as the father, this is the father, mother and the child rule, or we can see the FMC rule. Now what is the meaning of the FMC rule? What is the thumb represents the direction of the force on the conductor, this will show the direction of the magnetic field, and this finger it will show the direction of the current. So this is the Fleming's left hand rule. In all the three finger we are using the first finger, it is the magnetic field, the second finger is the direction of current, and the thumb it will represent the force on the conductor. Okay, so what is the Fleming's left hand rule? If you see, the thumb it represents the force on the conductor, the first finger it is the magnetic field, and the second finger it will show the direction of the current. And by the arrow diagram you can represent here magnetic field, force and the current. Now according to this rule, what we have to do, we have to stretch the thumb, forefinger and the middle finger of your left hand such that they are mutually perpendicular to each other. Okay, when like this you have to see they should be mutually, it means you can see that the 90 degree it is making here. So all three, these are the perpendicular to each other, and when they are perpendicular to each other, the first finger show the direction of magnetic field, the second finger show the direction of current, and the thumb will point in the direction of the force acting on the conductor. So this is the statement of the Fleming's left hand rule. If you see the Fleming's left hand rule, the thumb, this is the direction, this is the first finger, it will show the direction of magnetic field, this show the direction of the current, okay, and the thumb will represent the force on the conductor. So when all these three fingers they are mutually perpendicular to one another, they will be showing the different direction, the thumb showing the force on the conductor, this will be showing the direction of the magnetic field, and this is showing the direction of the current. So it is also called as the F, it is also called as the F, M and C rule. Now what is this? This is the father, mother and the child rule. F stands for the force on the conductor. What is the meaning of the F? This is the force on the conductor. M is the magnetic field, and C is the direction of current. So when all the three fingers they are mutually perpendicular to each other, the first finger always point in the direction of magnetic field. What is the first finger will show the direction of magnetic field, the second finger it will show the direction of the current, and the thumb will point in the direction of the force acting on the conductor. So this is the Fleming's left hand rule. This Fleming left hand rule we will be used in the next topic, that is the force acting on a current carrying conductor, and that force it can be calculated or it can be explained by using Fleming's left hand rule. So in the Fleming's left hand rule, you have to just stretch your forefinger, middle finger and the thumb. This is F, this is M and this is C. This is the F, this is F mean direction on the force, M this is the direction of magnetic field, and C this is the direction of current. So you have to understand this rule by stretching your all three fingers such that they are perpendicular to each other, and each finger will show the definite direction of force, magnetic field and current. Okay, and what is the application of this Fleming's left hand rule? We are applying in the force acting on the current carrying conductor. By that force can be calculated by using Fleming's left hand rule. Okay, or we can say is the father, mother, child rule. Okay, so at last again we are revising according to this rule. When forefinger, middle finger and your thumb, they are mutually perpendicular to one another, the first finger show the direction of magnetic field, second finger will show the direction of the current, and the thumb will point in the direction of the force acting on conductor. So this was the Fleming's left hand rule. Okay, now next we will study about what is the force acting on current carrying conductor in the magnetic field. Okay, the next we have to study what will be the force acting on the current carrying conductor in a magnetic field. Now when a current carrying conductor is placed in a magnetic field, it experiences a force, and this force is due to the interaction between magnetic field and current carrying conductor, and the force of the conductor can be calculated by using Fleming's left hand rule. Now what we are doing, we are taking a straight wire, okay, and in the straight wire, now this is the, it is rejoined from here so that we can see the movement of the wire here. Okay, we are keeping a horseshoe magnet here so that there will be generation of the magnetic field, and due to the current carrying current and this magnetic field, this is a current carrying wire, we have connected here with the, this is the battery we are connecting, the key it is closed and the rheostat. Okay, now what is the meaning of the rheostat? Rheostat is a it is a electrical elements, okay, which is used to vary the resistance. If we want to change the resistance, we can connect to the rheostat. Okay, now in this experiment what we are doing, this is the straight wire, a magnet it is there, and this magnet, so the direction of current is in this direction, and since the horseshoe magnet, this is the north pole and this is the south pole, so the direction of the magnetic will be in the this direction. Okay, so this wire, due to this current and the magnetic field, this wire which is attached here, it will be shows deflection. It means either it will be moved in the this direction or it will be moving in the backward direction. So this movement, it is given by the Fleming's left hand rule. You can find out easily direction with the help of the Fleming's left hand rule. Now how we can apply the Fleming's left hand rule here? If you see, you have to stretch your forefinger, middle finger and thumb such that this is the finger, it is in the direction of the, you can see the magnetic field is here, so direction of magnetic field is here. The current, it is going down. Okay, the current, it is moving down. If you see, this is the direction of the, this is the direction of current, it is going in the downward direction. Okay, so this is the direction of current, this is the direction of magnetic field, so the force will be experienced in this direction, so means this, it will be moving in the backward direction, and in the reverse of it will moving in this direction. Okay, so this is the application of the Fleming's left hand rule. Again you see, this is the direction of magnetic field, direction of current, and the force will be experienced, so this wire, it will be moving in the backward direction. Okay, and this magnitude, it can be represented by this, the magnitude of the force of the conductor, it is directly proportional to the current. More number of the cell you are using, more will be the current. Length, as you are increasing the length of the wire, okay, the force on the conductor will be more, and magnetic field, when the magnetic field be more, the force on the conductor will also be more. If suppose these are three equations, so when you join it, F is directly proportional to BIL. When you change proportional into the equal sign, it will be K. So this K value, it is 1, so you can write BIL. Okay, so this is the experiment of the force acting on current carrying conductor in a magnetic field. When a current carrying conductor, it is placed in a magnetic field, it experiences a force, and this force, it is due to the interaction between the magnetic field and the current. This is the direction of current, this is the direction of the magnetic field, so this conductor, it will experience force, and its direction can be given by the Fleming's left hand. This is the direction of magnetic field. If you can see, this is the magnetic field, direction of current, and force of conductor is the backward side, so this wire, it will move toward backward side. Okay, and this depend upon this force which is there on the conductor, it's on the three factors, that is the directly proportional to the current, directly proportional to the length of conductor, and directly proportional to the magnetic field. Okay, so this was this experiment. Since the wire, it is kicked by the current and the magnetic field, it is also called as kicking wire experiment. It is also called as kicking wire experiment. Okay, so this was the applications of the Fleming left hand rule. You have to apply Fleming's left hand rule to see the direction of the current or direction of the force acting on the conductor. This is the conductor. Due to this current carrying conductor and the magnetic field, this wire it will experience force, and it will, if we find out the direction, it will moving into the backward direction. Okay, so this was the force acting on current carrying conductor in a magnetic field.